Hello everyone and welcome to our week 3 discussion. Sorry this one's at a little bit of an unusual time. I had some incidents yesterday I had to deal with, so I had to reschedule. Given the holidays and so on, I thought I'd go ahead and just record this, share it out. Also, obviously it's available if you were to join, but given the short notice I don't really expect anyone to join. So again, welcome to week 3, an intro to big data analytics. Our agenda today, we'll go through the assignments, talk about the reading, and then talk a little bit about Spark, Databricks, and Azure Databricks in particular. So our assignments, as a reminder, we do have a late policy here at CTU. We will be going by this late policy. If for some reason you're not able to submit things within 7 days of the due date, do let me know, ideally ahead of time, and let me know what's going on so that we can figure things out. There are exceptions to our policy, which includes things that are extreme circumstances. So do review the policy, do make sure that you're following it, do understand that there will be a 10% penalty for late assignments. Where are we in the course? We're in Unit 1. Obviously, this is the third week. We're kind of wrapping up Unit 1 and moving into Unit 2. Unit 1 focuses on kind of an introduction of the domain. What is big data? Why do we do it? Why do we do analytics on it? Then the next unit moves into more applications of that, in particular around things like in industrial usage of in either manufacturing, financial industries, banking, government research and development, and so on. Also, we'll talk a little bit about the relationship between a data warehouse and a data lake and big data in general. Again, we are moving at the end of Unit 1. As of today, Unit 1's individual project is due. We are starting a break tomorrow, so on the 23rd. So there's no expectation of any kind of work being submitted between here and the end of that break. I do have a live chat scheduled at the conclusion of the break as well. Moving into a little bit about Unit 1, discussion board 3, you guys have already done. So the individual project is to basically look for an instance. It need not be banking. It could be an interest, a field that's of interest to you, and talk about how big data has had a demonstrated application in that domain. So find some sources that talk about either case studies or whatever it might be. Talk about some particular applications of big data. In the case of banking, you may want to talk about things like marketing, fraud detection, credit risk management, and evaluation. But if you're doing something in other domains, manufacturing, healthcare, whatever it might be that is of interest to you, maybe it's information assurance, whatever it is, feel free to take that assignment that direction. Again, though, it's due today, so hopefully you've already figured that out. Unit 2, we move into the industrial use of big data, and in particular around things like financial forecasting, research and development, and data warehousing. The first discussion board talks about how it's been applied to personal gene mapping, basically, in healthcare. Feel free to take this assignment a different direction. So you can certainly talk about healthcare and genes if you're so inclined. You can also talk about something that is of interest to you. But basically, again, the general theme is to talk about how big data has influenced that domain and what is the benefit, the business value that is being derived from that application. The second discussion board deals with around government regulations related to big data. In particular, the assignment calls that HIPAA. HIPAA is still quite relevant, so you may want to talk about HIPAA, or you may want to talk about something else. So again, feel free to be flexible with it. Your next assignment is to develop a 15-page slide presentation. Okay, the assignment is a bit vague, so hopefully you're watching this and are getting some clarification. The expectation is not a 15-page paper and a 15-page slide presentation, rather just the presentation. So you'll be using PowerPoint and creating a presentation that talks about the relationship of kind of this a marketing plan that might be used in relationship to big data analytics. And again, you can take it to the application of big data analytics, not necessarily just to marketing for increasing sales, but maybe it's around fraud detection, maybe it's around information assurance, whatever it is that is of interest to you. Feel free to take it that direction if you're so inclined. some resources for you. Some of these are a bit dated, but they give you a general gist of the material. The reading is in week 3 is chapter 2, and also in week 4, and some additional called out somewhat older references. Feel free to look for something a little more recent as far as the application of big data with application to some particular industry. With that said, I'll take a breath and then talk a little bit about what comes next, which is Spark. Whenever I was a student at CTU, one of the things that concerned me a great deal was that Spark was not really discussed much in any of the courses. And it has become a very compelling and very popular approach. MapReduce and Hadoop are still around. Hadoop is still in the ecosystem with various types of tools using it. That being said, Spark has become very, very popular of late. So it's an omission to not talk about it. There's some other things that we'll probably also talk about that I'll try to continually evolving this course, which is things around the massive loop parallel sort of processing that we're seeing that's becoming quite popular in quasi-database worlds such as Snowflake and Synapse. But back to the topic at hand, which is Spark. So the first thing is, well, what is it? And it's a reasonable question in general to start every conversation, is to try to figure out the domain, the problem it's solving, and so on, and how we got there. The underpinnings of Spark all come down to this concept of doing distributed processing on data frames or data sets. And that is what it is. It is a distributed processing system, first and foremost. It's about processing. That's the key word. It's not a storage system. It's not a database. It is a processing system. Now, it may enable you to look at things like a database, but it is unto itself not a database. It is simply compute. It's about processing the data that is stored somewhere. It enables you to separate that concept of compute from data. The initial versions of MapReduce and Hadoop kind of commingled those two things together. So your Hadoop cluster was also your storage cluster. We've since, even in the case of Hadoop, generally we're migrating away from that approach to using a more data storage approach with compute accessing that data storage. So in the case of the cloud, we typically store our data in something like a data lake, and then we process it using something that talks to that data lake. And the reason we're able to do that today, and we couldn't do it in the past, is because of improvements in networking and the way that we're building our data centers, in particular the way they're being built in the cloud. So we can now separate compute from storage, and that enables us to do things like turn off our cluster that does the compute, which is typically much beefier than the cluster that's necessary to do the storage. And the thing that is actually doing the storage isn't probably technically a cluster at all. It's some other sort of thing. A key distinction between Spark and MapReduce is that it is significantly faster, 1 to 2 orders of magnitude faster, in fact. So even at its slowest, whenever it's having to deal with things on a disk, it is considerably faster than MapReduce. It also allows you to do things like iterative programming, whereas MapReduce, in its purest form, is essentially one pass through. So it is literally applying a mapper and a reducer to your data. It's not intended to do something like machine learning, where you do iteration or neural network processing and so on. The underpinnings of Spark are these things called resilient distributed data sets, and there's a lot in that name. Resilient and distributed are key defining characteristics, right? That means that they are able to handle failure. So if for some reason the node in the cluster that is processing a particular portion of the data fails, then something else can be done to spin it back up. So another node in the cluster can pick up what it had, so it knows the thing that is managing this processing knows what data that cluster element was assigned, and so it can essentially assign that data to some other node in the cluster, and it knows the transformations that need to be done to it. So it can do those transformations and then pick up and combine things together after the fact. It does contain this concept of lineage, and you can keep track of what's being done to the data set. And And that's because it's basically constructing a directed acyclic graph for you. So a DAG is being used to tell Spark what to do. So even though you're writing a program in maybe a language like Java or Python or whatever, at the end of the day, it's getting compiled down to or interpreted into a graph that is then evaluated by the cluster. It does support both batch and streaming. The type of streaming in Spark today is called structured streaming. It's not a true streaming system in the sense of traditional streaming approaches. So it doesn't, output is not produced by the arrival of input. And that's a kind of a key definition of a streaming system. So if you're dealing with something like a complex event processing system or the like, the output of those systems is because of the arrival of data. And a structured streaming approach, it uses a micro batch architecture, which basically, as the name kind of implies, it's little batches. The job doesn't really terminate per se, but it's like a while loop with a sleep or something, right? So it does the work and then it pauses for a while and then does more work, and hence the name micro batch. It's not exactly streaming, but it's usually good enough for most things. And that's why we use it, is that it does satisfy the requirement of most organizations to actually do streaming. So, talked about Spark, and Spark is cool stuff. If nothing else you take away from this, take away that. Spark is cool. The next sort of thing to think about is what is Databricks. So Spark was created by a set of pretty bright people in Berkeley. They recognized what they had created was cool, right, and very powerful and compelling. So what they did was set out to industrialize it or productize it. So they created Spark or Databricks, which is Spark is open source. So anybody can go out and get Spark and build it and run it and so on. Databricks takes that concept to that plus some other stuff. And it's kind of a common pattern you'll see in the open source world, is that things are available for free via the open source license. However, if you want some sort of support or whatever it might be, there's a commercial variation of it that you often use. So that is what Databricks is. Is it a commercial company that is founded on the concepts of Spark being its primary processing engine. It's available on Azure, AWS, and GCP. I need to update my slide because GCP is a relatively new arrival. And it does enable this concept of collaborative notebook-based development. And what that means is notebook interfaces have been around for a while. Think Jupyter Notebooks. If you're unfamiliar with Jupyter Notebooks and you're a big data analytics person, become familiar with Jupyter Notebooks because it's important. The basic idea of a notebook is that you have this concept of cells inside of a notebook. Each of the cells can contain either code or documentation via Markdown. Markdown is a type of HTML-like sort of language that is simplistic for creating documentation inside of your code. So you commingle together the code, the output from the code, and the documentation into a single experience that is web-based, and that is a notebook. You can write those notebook cells using Python, Scala, R, or SQL, and you can actually switch languages between cells if you're so inclined, and I'll talk more about that in a little bit. One of the key things that Databricks does is they make it drop-dead easy to create a Spark cluster. Creating Spark and installing Spark is not that hard in general, but anytime you start dealing with things like provisioning virtual machines or containers or whatever technology you're using, managing those things, detecting when they're getting sick and need to be restarted or things need to be done to them, adjusting how many of them you have based upon the capacity and the amount of work that you're trying to accomplish, those are the things that Databricks does for you. So it's all about management, scaling, security, all of the stuff that you would have to do if you were doing it yourself. It does integrate with Git repositories and can enable you to do things like continuous integration and continuous deployment, which is something that is essential in today's engineering sort of environments. And the key thing about Databricks compared to a lot of historical companies is that it is all about consumption. They make their money when you use their product on the cloud platform of your choice. They do have a professional services organization, but it's primarily about making sure that you're able to use their stuff. So it's not about like a lot of companies where professional services may actually be the bigger portion of the organization. It's really an enabling technology. One of the key things about that sort of revenue model is that they are driven to continually be improving the product and addressing any kind of issues that might exist, because frankly, people can go away and use other stuff. And there are lots of competing technologies to Databricks. And in particular, things like Azure Synapse, Snowflake, and Dremel, and so on. There's lots of competing sort of organizations. So the next question you might be asking is, what is Azure Databricks? Because I said that earlier on in the discussion. What is Azure Databricks? And it is the first third-party offering to be integrated into Azure. There may be additional ones. There may even be some that have came along since I made this statement. But it's a separate company, but you can't really tell it whenever you're in the Azure portal. It uses Databricks. The same code is basically the same across all of the different cloud offerings. However, there are some optimizations that have been done for Azure inside of Azure Databricks. In particular, things like it's integrated tightly with the directory services, not domain services. I need to correct that. So the directory services use things like pass-through authentication. What that means is that if you're using a notebook and you're editing and running code, and maybe that code is accessing a data lake, whenever you run that code, it doesn't run as some administrative super user sort of account. It runs as you. And that means that the code that you're running has your permissions whenever you go to retrieve things or update things inside of a data lake or or lake house sort of architecture. And what that means is that you can have essentially folder level permissions associated with it. You might, or file level actually, but you're not going to go down to row level. That's going to require some other technology. It is highly integrated with things like Azure Data Factory and Data Lake Store and data storage in general inside of Azure. And also you get one bill. So if you go into Azure, you create Azure Databricks, you're not going to be getting a separate bill from Databricks. It's one thing that comes in, so you can see based upon the same sort of tags and so on of who's doing what whenever you go to pay the bill. So how does it work, right? So as I mentioned before, there's these different, almost like kernels inside of Jupyter, right? But the distinction is that you can have each cell in your notebook be a different language if you're so inclined. What that lets you do is use the language that is the most appropriate for what you're trying to accomplish, or the language that your organization has the strongest proficiency in, and then still be able to go to the others if you have to. So if perhaps you've got a bunch of people that are very strong in SQL, you can use SQL as your language of choice inside of your notebook. And if you have to do something else like run some Python code, you can. The crossing of those things is via essentially a table construct. It's not a table in the sense of a database table, but it looks and smells like one. So again, Databricks is using this notebook paradigm. You go into this web editor and author your notebooks, debugging them as you go through the process of writing them. And you get output on each evaluation of each cell in the notebook. Then once you're done with that process, you can actually schedule those notebooks and run them as jobs. And what that means is they can be orchestrated, called, and so on, very similar to like a function or a module in a traditional programming language. You can also trigger a notebook from things like Data Factory. So you can do things like build a pipeline that ingests data from some data source and lands it into the data lake, and then invokes a Databricks notebook to do a data engineering exercise of refining that data and perhaps writing it out to someplace else in the lake as well. And the key thing there is that you can tailor it to what suits the particular need. Sometimes it's really easy to do things in SQL. Sometimes it's very easy to do things in Python, but those two things are typically not the same set of things. So that's why you might particularly want to mix languages. There's also this concept of a table as being the means of communicating. There are also temporary tables that go away essentially when the cluster reboots. But the key distinction, if you want to learn more about Databricks in general, is this concept of a managed and unmanaged table. All that really means is that if it's managed, it's kind of in line. So if you delete it, the data that's stored in that table goes away. Because of that, we typically don't use managed tables. What we do instead is typically have the files in a data lake, and we point a table similar to an external table in something like Hive to that directory, and we treat it as a database, essentially, as a table. So when you delete an external or unmanaged table, you don't actually delete the files. You just delete essentially the pointer that's referencing it. So you're not losing data, which you might do if you're not careful with a managed table. So takeaway from that is, typically speaking, you want external or unmanaged tables. So what does it look like? And so this is a screenshot of Databricks Community Edition. I would recommend using Community Edition for your assignments in this course, but it's up to you. It is free. Don't pay for anything. Don't sign up for any trials with a cloud provider. It is a little tricky because they obviously want to encourage you to sign up, but you don't have to. There is a way, if you read the screens carefully, to get it for free. The Community Edition basically gives you a single node cluster. What that means is there's a driver node that's kind of a managing node, and a cluster, and in most of your clusters you have one of those and a lot of different workers. But what you do in a single node cluster, which is what the Community Edition is those are one and the same. So you don't really do truly distributed stuff, but you can write code that seems like it would be doing distributed code, but it is still running on a single computer. We do that sometimes for lower cost reasons in the real world, but it is a nice free service that's available for you. You can go in and pretty close to what you get in most of your Databricks environments. So do take a look at that. So community.cloud.databricks.com, or if you Google Community Edition Databricks, you'll find it as well. So an example notebook, not the most exciting one you'll ever see. I basically took some data from data.gov, downloaded a CSV, uploaded it into a table in Databricks, and then wrote a select count star from a table, grouping it by full file name and ordering it in by the name of the full file name. So you can see simplistic aggregation of it. Also, it looks like it's ordering it ascending in the top, or no, I've scrolled down. Also, you can, inside of the Databricks UI, and this is something that's kind of cool, the results can be rendered as either a data frame, which is what you see in the top half of the screen, or some simple visuals, which you see in the bottom. Databricks isn't going to win any awards for the most outstanding graphics, but it gives you a pretty good sense of what it looks like. It can handle things like bar graph, histogram, and a few other things. It's not Power BI, it's not Tableau, but it is a nice unified simplistic visualization that lets you see what the data looks like without having to do some sort of export and import thing. That being said, Databricks does support, especially Azure Databricks, integration with things like Power BI and Tableau, to the point of actually doing some pretty intelligent processing of the things that are stored in your data lake. Okay, and if we think about Databricks from a big data analytics perspective, it is very relevant in that Spark is one of the more popular big data frameworks in use today. These frameworks are all about simplifying the process of constructing and managing and running distributed applications. So it is quite relevant from that regard. It's also worth noting that Databricks has recently been working on rewriting the Spark engine they use to have the alternative of doing a high-performance C++ based version of Spark versus the traditional Scala-based approach, and it is significantly faster. There's lots of compelling reasons to look into it. And it's gaining continual usage, and I think in part of what's driving that is it's expensive to run Hadoop, especially in the cloud. An example being HD Insight. Azure HD Insight is an offering that basically creates a Hadoop instance and lets you manage it via a web interface, very similar to whatever you do with the rest of the Azure services. But the problem with it is you pay for that cluster as long as it exists, regardless of what it's doing. So the very fact that it exists costs you. So even if you were to do something like turn it off, you're still going to pay for it. Also, one of the other factors that's driving adoption, I believe, of Spark is recently Cloudera, or fairly recently, Cloudera purchased Hortonworks. And this is a general theme across the Hadoop ecosystem is bigger companies are buying up littler companies and consolidating. So we're seeing a reduction in the number of distributions of Hadoop. Hortonworks used to be a pretty popular, basically vanilla plus a little of Hadoop. So they take Apache Hadoop, package it up, support it, but it was pretty close to the original sort of open source edition. Cloudera takes a different approach. They highly customize the open source community stuff, but they also charge considerably higher licensing costs than things like Hortonworks used to do. So people have been migrating away from Hadoop, MapReduce, that pattern, largely for that particular reason, is that Hadoop is quite expensive. Also, data lakes are pretty cheap. It's one of the cheaper ways of storing things. You can actually even go cheaper and just store in object stores. Within side of Spark, you can talk to most of the major technologies. You can listen to a Kafka queue or topic if you're so inclined, and so on. And the fact that it is a unified framework that handles both batching and stream processing, and the code is fairly close. There's a few differences here and there, but it's really close. In fact, the parts that are different are kind of the bit where you create the stream or read from the stream and write to the stream. Other than that, it's pretty much the same code. So that the fact that it is a single sort of framework is quite compelling, and that's one of the things that drives adoption. If we think about them in terms of databases, Spark can read and write to databases, and it's not quite the same level of support, perhaps, and optimization that you might see of dealing with things like a data lake, because it's a lower priority. But you can definitely connect to a database, read it, write it, and so on. Things like pass-through authentication, which you can get with a data lake, so that the operations are done on behalf of the user, not on behalf of the service account that runs. You don't really get those as much in a database world. You can do user authentication via connect strings, but it doesn't have like the equivalent of SQL servers, essentially Active Directory federated authentication. You can look at it as a way of running analytics queries, transformations, and visualizations, because you can run SQL inside of Spark, and it is very similar to the SQL that you might use in something like MySQL. It's pretty close. It does store this concept of things that look a lot like tables, and things that look like views. Indexes, not so much. So you have to do some other stuff if you want to try to improve performance. You don't really do indexing. You do things like partitioning and ordering, or Z-ordering within a partition. There's not really the same thing as an index. And one of the key things is that if you know SQL, then it's an easy way to start accessing big data. Moving into Databricks. Again, these are a bit of a marketing sort of take on things, but it is a unified data analytics platform, and that's the key thing, unified, and it does use Apache Spark as the underlying engine. Delta Lake is a layer on top of a data lake that enables things like ACID compliance of sorts, and time travel, optimization, and more importantly, read-write and upsert sort of capabilities, something that you can't really do natively to Parquet. You overwrite, you don't update. And you don't really update in Data Lake or Delta Lake, but it kind of does it for you, and it looks like it, and then eventually you realize those changes you're making by essentially optimizing it and rewriting your files. Also, Databricks supports MLflow, which is a machine learning oriented way of storing the results of experiments and models, so that you can actually be able to look over what is the best set of hyperparameters that you use whenever you're tuning your model, and then pick a model and deploy it to a production sort of workload with like 1 or 2 lines of code. So pretty cool technology. It is very, Databricks has a lot of companies. It's gotten a huge valuation. It's probably going to be doing an IPO in the next year. So what is Azure Databricks? It's basically a Microsoft invested heavily into Databricks, the company. So they have put a fair amount of money into it. They've also done a lot of work of seamlessly tying things together. So it's really hard to tell which is which. And it does work natively with all of the Azure services such as Power BI, SQL Data Warehouse, which is now Synapse, Cosmos DB, Blob Storage, data lakes, and so on. And you do get the best of enterprise level security. So Active Directory integration, you get compliance, and so on. Basically, it's popular, and that's the key thing to take away from this slide. Lots of people are using it. Lots of workloads are going through it, and it is quite useful. One of the things that I wanted to do in this discussion also was start talking a little bit about architectures. That's another gap I noticed in this curriculum. We don't necessarily talk a whole lot about architectures. This one's a relatively simple sort of thing. It's basically showing you data comes in on the left side and goes out on the right side. That's an ingestion, and then serving is what we typically call those. In the middle is where the magic is happening, and there's some underlying foundational stuff such as the Azure portal, DevOps, and making sure that you've got some security in place. Those are kind of foundational things that are necessary. Looking into it a bit more, this is a typical sort of design that you'll see. And the way this works is we typically view them as moving left to right. Left is ingest, right is serve. In between the two, we typically do some processing. So what we're showing you here is that you've got both the streaming and the batch sort of world coming in. So Data Factory drops things in the data lake. You can listen to Event Hub, IoT Hub, or Kafka as far as having a Spark structured streaming job running this listing there. That job will likely land things in a data lake, although it need not. But it definitely does some sort of processing to it to determine maybe something needs to happen, or maybe there's something interesting that needs to be filtered out. And that's exactly what you're trying to do whenever you're doing stream processing, is determine what is interesting, what is not, what needs action taken, and so on. Sometimes you'll persist it, sometimes you won't. Depends upon the type of data and the value of that data. Once it's landed in the data lake, your next step is typically to go through and start doing some sort of analytics on it. And then also you'll typically be pushing it out to some sort of serving layer. That can include Databricks being the serving layer itself, given a relatively recent addition of SQL endpoints that are highly optimized using that C++ engine I mentioned, which has the name of Photon, to basically handle the processing. And also you can potentially push out things to more operational sort of databases such as Cosmos DB, which is a multi-model database that allows you to store data as either a document database, a graph database, column database, and so on. So it can be viewed as a replacement for lots of different types of databases. And then at the end of it all, there's typically some sort of application, either something like a Power BI or Tableau or something, serving the data. Also, one of the things we typically do inside of that data lake is go through the process of going from a raw sort of format over to a Delta Lake format, which is essentially Parquet plus some JSON files. So when we talk about how this typically works, you bring in data, you land it in the raw format. That raw format is the format that you got it from the source system. And the idea here, this is a data lake architectural sort of concept more so than anything else, is with data lakes, we land raw and then we refine it as we need it. So you extract it from whatever is the simplest way to get it from the source system. Maybe it's a CSV, maybe it's some old school thing like a DBF, so a database file that's used by DBase or something. Who knows? Maybe it's Access database, or maybe it's a binary format that the source system uses and you want to grab it. The point is, you do as little as possible to get it into the lake. Once it's in the lake, then we go through this concept of zones of refinement. Databricks uses the concept of bronze, silver, and gold. Bronze is basically simply taking it to a Delta format. When you move into silver, it's typically taking it over to where it's viewed to be business ready. So the idea of silver data is that you can make business decisions based upon it with some degree of trust that it is correct. A key concept inside of data lakes is that on ingest, we don't trust the data in raw. We expect it to be noisy. We expect it to be errant. We expect it to have challenges. We refine it, we clean it up, we transform it so that it becomes usable, and we move that into what's called the silver, so it's business ready. So the silver zone is essentially business ready. The recommendation from Databricks is that that is stored in Delta format as well. So again, Delta looks a lot like a database. It's not really a database, but it's essentially a set of folders on a data lake with things like a journal that lets you know what needs to be done or has been done to those files, and also can do things like optimize them so that you don't have problems with what's called the small file problem, which is any kind of big data technology typically does very poorly with tiny files. You want bigger files, but not huge files. So the point of Delta is that it can optimize to that sweet spot, so that the thing that's not too big and not too small. So the Goldilocks type size file, right? So the just right. The next step is to move over to Gold. Gold typically is a degree of aggregation has been done. So you're typically joining files together, joining tables together to produce things that are for a business purpose. You may also be doing things like doing some data science on it. And then the last step is to typically make this available either through something like Polybase, where you can pull data into Synapse, or maybe it's you load it into Cosmos DB for consumption if it's a low latency sort of challenge or that you're addressing. But this is the basic concept that you'll see, and Databricks has recently called this the Lakehouse architecture. Whenever we talk about the batch processing flow, it's pretty much this. And this also is very similar to a Lambda architecture. Lambda architectures are the idea that you have a fast path, which is things that come in near real time, so streaming. Also, you have a slower path where you may ingest things in a batch mode, and you may also save that fast path and then do some fix up on it over time. So the idea is that you might answer a question near real time, but maybe it's not the perfect answer. You come back later on and you give a better answer. So it's giving you an answer off the top of your head versus thinking about it for a while. You can think of it that way. Here we see the streaming path highlighted. Again, Databricks is writing most of the likely to a data lake store. And then also you may be updating the data warehouse near real time as well. When we move over to the ML, the machine learning sort of flow of things, generally speaking, ML is going to be pulling off of the silver zone most of the time, but it need not. Part of the benefit of a data lake architecture is that if you have data scientists that are skilled in the art and can access data that hasn't been through a rigorous refinement sort of process, they can get to the raw data if needed and know how to do it and know how to not trust it and so on. That's one of the business values of using a data lake architecture. But the basic idea here is showing that oftentimes you're going to do some training, prepping, and then eventually you're going to probably push out the model for serving, likely through something like Kubernetes. And the BI workload is going to be taking a look at the kind of the bottom side of things. They're likely going to be accessing either Databricks to connect to a data lake, oftentimes in Delta format, or they may be talking to Synapse because of performance reasons. You may be using things like analysis services to increase performance. So with that, I've reached the end of what I have to talk about. Thank you for watching. Stay safe. I hope you have a good break, and we'll talk again soon.